So welcome back to Calc 2. This is Monday morning, April 20th. Today, this video will cover the last new material that will be presented this semester. This video is for Wednesday's class. There will be an assignment made that will be due on Friday, and then I'll make one more video about review for the final exam. And towards the end of the week, we'll focus our attention on the final exam, what to expect, topics that will be included, and so forth. So the last topic we want to talk about, it's in Chapter 12, Section 1. The material for Wednesday's homework for today's class period, posted last week, was on parametric equations, and I hope you had a chance to dig into those and find out what's going on and look at some of the examples I gave you. And today we want to apply calculus to curves defined parametrically. There are a lot of things we could do. There are two things that I'm going to do, and that is we're going to talk about the slope of the tangent line. We can think about that also, as we know, as the rate of change, y with respect to x. And then we'll talk about arc length. We learned a little bit the arc length of on the graph of a function in Chapter 6 earlier this semester, and now we want to extend that concept to finding the length on of a parametric curve between two values of the parameter. This is a concept that's going to play a major role in things you do in Calc 3. So we want to get you familiar with it. So when you see it again in Calc 3, you'll be, you have a head start. You know what's going on, and the notation it's identical the way you're going to use it there. Okay, although you'll extend it using things you learn in Calc 3. So here we go. 12.1, the introduction and the calculus is all rolled into one section, unlike polar coordinates in our textbook. So we covered the first part of section 1 on Friday's video posted for today's class, and now we'll cover most of the rest of it. So here we have a curve given parametrically, a function controlling the x coordinates, another one controlling the y coordinates, with generic parameter t. It follows from the chain rule that the slope of the tangent line, which is the rate of change of y with respect to x, when x and y are given parametrically, then it follows that the derivative dy dx is just the derivative of y with respect to the parameter divided by the derivative of x with respect to the parameter. So a very intuitive result. Right here, we don't have to think too hard about it. I think that maybe what we would guess would be a good expression, a valid expression for dy dx. Now, for some reason, when I use it, I tend to want to get my derivative of x in the numerator. I'll try to be careful, but that's about the only mistake I tend to make with it, and so don't you make that mistake as well. So there it is, dy dt over dx dt, and we can think of that as a slope of the tangent line. We can also think of that as the rate of change of y with respect to x. And so I want to just give an example. I've picked a curve here. The x function is t squared plus 1, and the y value is t cubed minus 12t. We'll think of this as being defined for all values of t. With polynomial expressions, they certainly, x and y are defined for all t. And we want to see what calculus can tell us. We'll also get a chance to practice what we learned before, just about the nature of parametric curves. So I've asked 5 questions about this curve. And as you know, you can sketch the graph on your calculators. Maybe they're still in parametric mode because of what we did on Friday. And so we'll do some analysis, and then in the end, we'll come up with an idea for the graph, and you should check and see with your calculators, does the graph we come up with, does it look like the one your calculator thinks? And if so, we'll have a little more information. You can take the information we have and kind of think of it in terms of the graph that shows up, both what we'll do yeah, set part E, I've asked for us to graph the function, and we'll graph it using what we know, and then we'll graph it on our calculators and compare. So the first thing I've asked is to find all x-intercepts. That's not a calculus question, that's an algebra question. The x-intercepts are all of the values where y is 0. On the x-axis, all the y coordinates are 0, so we'll set y equals 0 and solve, and that will get us t values. It'll give us values of the parameter. Those are not the x-intercepts. Then I'll take those t values and plug them into my x equation, and then I have the x-intercepts. So for part A, again, an algebra problem, not a calculus. We're going to set y equal to 0. Well, y is t cubed minus 12t. Set it equal to 0 and solve that equation. Normally third-degree polynomials are hard to solve, but this is a nice one. It only has cubes and t's of the first, so factor a t off of that, and we get t squared minus 12 equals 0. And so you can see we get 3 t values, 0 or plus or minus the square root of 12. So to actually find the x-intercepts, we need to take those guys and plug them in. So when I take the first one, t equals 0, plug them in over here, you can see easily we get x equals 1. So one of our x-intercepts is x equals 1. When I plug in plus or minus the square root of 12, notice we immediately square that sign away. So even though there are 2 t values, there is only one x-intercept. Plus or minus the square root of 12 squared plus 1 equals 13. So 2 different t values. The square root of 12, which is 3.5-ish, and the negative square root of 12, 2 different t values, the same point, the point 13, 0, x-intercept 13. Means that this curve passes through that point 2 different times. Now, if we hadn't done the examples we did on Friday for today's class, then that might seem a little bit weird, but if the last example I drew with the trig functions, you can see that curve passed through lots of different points more than one time. So, we've seen it before and we understand how it can happen. And like I said, I'm pretty, we're going to sketch the graph. We'll keep this in mind. There are 2 different t values. I think what I'm going to do is erase this side so we can keep track of this information as we get it. And maybe let's write our equations up here so we don't lose track of them. T cubed minus 12t. So it's written right there, the y. And use this space as well. So up here, we'll keep track of what we learn as we learn it. So in order to draw an axis here, we can see that x is always bigger than or equal to 1. So all the action is over here. We found these x-intercepts out at 13. I don't think there's going to be anything interesting where x is bigger than 13. So let's kind of think of 13 as our maximum value over here we need to worry about. And we know that the curve passes through this point at 2 different t values. Let's put a big blip there. See, I kind of know what the curve looks like, so I'll write it over here. I think it'll be out of our way. It goes through this point at 2 different t values, plus or minus the square root of 12. And remember, we also found a x-intercept over here at 1, which was t equals 0. Okay, so that's what we know so far. 2 t values here, 1 there. So part B, I asked for the horizontal tangents. So for part B, we need the derivative dy dx to be 0. Well, if you think about it, dy dx as a fraction, we need the numerator to be 0. So that's how we're going to find horizontal tangents. And there's one thing we need to worry about, and that is we need the numerator to be 0, but not the denominator. If they both are 0, then, you know, that's that 0 over 0, that unpredictable case. And, you know, so we'll find out where dy dt is 0, and we'll quickly check and make sure that dx dt is not also 0. I think we're going to be just fine. So dy dt is 3t squared minus 12. And factor the 3 off. And we get this really wonderful textbook kind of problem, t plus 2, t minus 2. So there are 2 points, 2 t values, which may or may not correspond to 2 different points on the graph. You know, it could be one of these that passes through twice. And these points have something in common, and that is they have a horizontal tangent. Let's quickly check. We get plus or minus 2. And notice the denominator of the derivative, if I wrote it out, would be dx dt. That's 2t, and it's not equal to 0 at plus or minus 2. So there really are horizontal tangents at plus or minus 2. Let's find the points on the graph. If t equals 2, then x equals 5, t squared plus 1. And y is equal to 8 minus 24. Negative 16. And if t equals negative 2, x is still 5. Square that minus sign away. And y is equal to minus 8 plus 24, plus 16. So different points. Same x coordinate, but different y coordinates. So let's see. 5 is probably about right there. And we have a point up here. 5, 16. You can't see that. I can write it underneath. Actually, let's write it this way. Perfect. And then there's another point. It's down here. I think we're done with this. I'll erase it. And negative 16. The t value here is the one that got us 16 was negative 2. And down here it's plus 2. Okay, so we have a little more work to do, but think about this. When t equals negative square root 12, 3.5-ish, we're here. A little bit later, that is negative 2 is beyond, bigger than negative 3.5. We're up here, and then at 0, we're here, and then at t equals 2, we're there. So you can start to see how this curve is going to go. Well, part C, repeat for vertical. Well, these are super easy. Part C. So for vertical tangents, we need the denominator. We need dx dt to be 0, while dy dt is not. Well, dx dt is 2t. If it equals 0, t equals 0. And so we see the point we've already identified in x-intercept. That gets us to point 1, 0. So we have a vertical asymptote here. Sorry, vertical slope. Let's just dash it in. And the curve is wholly contained to the right of that line. Part D, find the slopes at the x-intercepts. So haven't written an expression for the derivative yet. We've written both of its parts. Dy dx is 3t squared minus 12. 2t, and then what we want to do is plug in the t values at the intercepts. We already know the slope at this one. D asked us to do it, but we've already done it, just luckily. But we have these guys over here. So let's plug in. I think we can do these all at once. Plus or minus the square root of 12. In the numerator, we get 24 for both of them. Square root 12 squared is 12 times 3 is 36 minus 12. And down below, we get double the t value. So we're going to get plus or minus 2 square roots of 12, which is plus or minus 12 over the square root of 12. 24 divided by 2 is 12, but that's just plus or minus the square root of 12. This is the square root of 12 squared. Cancel one of them out. So the slopes are plus or minus the slopes at the intercepts are plus or minus the square root of 12. And the sign of the slope corresponds with the t value. We didn't have to change it anywhere. So when t equals negative square root 12, the slope is negative square root 12 as well. Negative 3.5-ish. Well, negative means it's going down. 3.5 means it's pretty steep. So let's draw it sort of like that. Slope of negative 3.5-ish. And when we come back around to this point, at t equals the square root of 12, now the slope is positive. So the tangent line is going to look sort of like that. Okay, now I think we have enough information to draw the curve. We found all the x-intercepts. We found all of the points where the slope is horizontal. We found all of the points where the slope is vertical. And so we can be pretty confident. See how well I can draw this. Curve is going to be coming up. We could do an analysis of the sine of y. Let's do it just because we haven't done these sort of things for a while. Y is going to change sign to 0. And at the square root of 12 and the negative square root of 12. And it's going to go positive, negative, positive, negative. The sine graph. Our old friends from before. And yeah, we factored it right here. So factor this difference of 2 squares, we get a square root of 12 in there, and you can see those are the signs. So below negative square root 12, the y coordinates are negative. The graph is below the x-axis. As soon as t passes through negative square root 12, the y coordinates become positive. So this graph is the sign of the y coordinates. And then we hit 0, t equals 0, and they turn negative again. So here we go. We're negative. We hit the intercept with slope like that tangent line. We come up, we turn positive, y does. I'm heading towards the label and not the point. We have a vertical tangent up here. And then we have a horizontal tangent there, a vertical tangent here. And then t becomes positive and y turns negative. We go down here. We have another horizontal tangent we're heading towards. And then we leave the horizontal tangent. We hit the x-intercept with slope like this line, and then it just takes off. And the orientation is just exactly how I drew it. So as t goes to minus infinity, it just shoots down, a third-degree polynomial pretty fast. It comes up, it hits the intercept, and then we have some interesting behavior here for a while, and then the function takes off again. So it's going to minus infinity, plus infinity there. I guess you can see the whole graph. I think it's believable that this graph up here is a mirror image if I were being super careful, they would look exactly alike. You know, polynomials aren't all that complicated. But it's an interesting curve. It's a curve we've never seen before in rectangular coordinates or polar. And it kind of shows you some of the ways that parametric curves can add variety. It shows us how we can use information about the slope of the tangent line, which is the whole point here, to use that in conjunction with what we learned before about parametric equations. And so we get the super beautiful curve. It looks kind of like a fish, like a puffer fish or a blowfish or something. Maybe we can label it. Anyway, there you go. That's my first example. So our second application of calculus, as I mentioned at the beginning, is to take a look at arc length. And let's quickly review. In chapter 6, back in, I don't know, late January, February, we derived a formula for the length of a curve from x equals a to x equals b. You travel along the curve, and this is the integral we derived using Pythagorean's theorem and some things we know about calculus. Now we want to extend that idea. Now have a curve given parametrically, not the graph of a function necessarily, but a curve given parametrically. And I can travel along this curve, start somewhere. Let's start at this point, A, and we'll end up at this point. I travel along the curve, and I want to know how far have I gone? What's the length of that curve? And because of the curve, geometry can't tell us. You know, if it were a line, then, you know, the distance formula, bingo, we've got it. If it were on a circle, then we know how to measure portions of a circumference of a circle. We could do that. But if it's any other curve, geometry just sort of gives up. It says, I don't know. And so, because of our experience in chapter 6, we know that maybe what we can do is to break our interval from t equals a to t equals b into equal pieces and estimate the length of the curve on each piece. Maybe we could be so lucky as to write that in the form of a Riemann sum. And if we do, then, you know, we can turn it over to an integral. So I think I told you, and when we finished chapter 6, that we would talk about Riemann sums a couple more times. And we've done it. Actually, the calculus professor, I used his video for area and polar coordinates, but he found a Riemann sum. And here we'll do it again. Because it's so much like what we did before, we'll skim over it pretty quickly. So here's a typical piece of the curve if I break it into these n equal parts, and we'll call the length of the curve the actual length, L sub I, and I can approximate it with a straight line distance. And so here's a right triangle, the length of this side we'll call delta x, and over here we have delta y. And so by Pythagorean's theorem, if the straight line estimate is the square root of delta x squared plus delta y squared, which ought to be a good approximation to the actual length, L sub I. And now we need to make this look like a term in a Riemann sum, exactly like we did back in chapter 6. So here's what we're going to do. Multiply by, t is my variable here. It controls the movement. And so, you know, I've labeled here, we're going from t equals a to t equals b. So we're thinking of t as a variable. And so what I really need to get a Riemann sum is a delta t. I'll force it and then pay the price. I need this one in the numerator. I don't need this one. But, you know, I got to multiply by 1. Now take that delta t, shove it under the square root, and we get things that look like this. We'll combine, we'll distribute it across the plus and combine it with the x and then the y. And the mean value theorem, exactly like we used here, says that delta x over delta t can be written as, I call this function f. Let me change the expression underneath there to be consistent. We didn't call them f and g, we call them x and y. So, and there are so many variables, instead of using prime for derivative, let's just write the differential. So this would be dx dt. At some, evaluated at some point, ti star, and this would be dy dt. Again, evaluated. And now you can see we have perfect Riemann sum. We have some function on defined at some point on the interval. These guys would be evaluated at a t value we choose in here. You know, maybe we choose that one right there, ti star. And then we have our delta t at the end. So, you know, we can gloss over some of this because we've done it before. We've done it almost identical when we derived this back in chapter 6. So anyway, we end up with this formula. And whether you understand Riemann sums or not, you have my permission to use that formula. Okay. So let's do some examples. All right, as an example of arc length, I am going to work through number 88 in the exam, in the textbook. So if you remember, back when we studied arc length of a function back in chapter 6, most of the antiderivatives were complicated because of the nature of the formula, the square root of 1 plus f prime squared. It makes finding the antiderivative hard. And the same thing is true here. Dx dt squared plus dy dt squared. Now take the square root of that. And what are the chances we can find an antiderivative? Of course, there are several examples in the book where you can. I don't like them all that much. I think some of them are, the curve is actually a line, in which case we don't need calculus. All we need is the distance formula. Some of the others are circles. And because we know how to measure parts of circumferences from geometry, we really don't need calculus for that. And so I've picked one that we don't know the curve. And I've drawn maybe a picture of it. I didn't dig in super deep. I didn't graph it on my calculator. I used some information we had to come up with the curve. And then, you know, we'll work through, there are some kind of surprising, or I don't know, I don't want to say difficult, interesting things that happen along the way. And we'll talk our way through it. I haven't put all the details on the board, and so maybe you'll need to pause the video and work some of them out for yourself and see what you get. I haven't actually checked to see if my answers are right, but I feel pretty good about it. So number 88, the curve is x equals sine t, y equals t minus cosine t. And we're looking at values of t that go from 0 to pi over 2. I paused for a second on the t because with that t there, we don't know the graph of this. If you take the t away, it's a circle. Cosine t minus sine t. The minus sign, all it would do is maybe affect the orientation of the circle, but that's a circle. But now we put the t in there, and well, man, we've never seen anything like it. And an interesting consequence of it, as t goes to infinity, so does y. This piece goes to infinity, and this piece just a little bit of noise, so to speak, around t going to infinity. So a very interesting curve to think about as t goes to infinity, but not for this problem, because they tell us in the book t goes from 0 to pi over 2. So I made a little chart because we don't know the curve. I haven't seen it before. I made a little chart to help me figure the values. And I just plotted the endpoints. Then we'll think about in between. When t equals 0, the left-hand endpoint, x is 0, sine is 0, and y is equal to -1, 0 minus 1. So we start out at this point. Didn't draw my orientation angles, arrows. And at the endpoint, when t was pi over 2, sine is 1. And the cosine is now 0, so y is pi over 2. So we end up at the point 1 pi over 2. Pi over 2 is just a little bit bigger than 1.5, so up here somewhere. And I don't know what the curve does. I didn't, like I said, I didn't graph it, but I know it's got to get from here to here. I know the sine values just gradually increase, right? In the first quadrant, sine just goes from 0 to 1, and nice steady increase. Kind of slows down at the end, so that's why I've kind of drawn it like that. It doesn't really matter because the formula, we can make it work. And for the formula, we need to know the derivatives. So easy enough, dx dt is cosine t, dy dt is 1 plus sine t. Square them, add them up. And okay, so I did some algebra here. When you square this thing out, remember there's that middle term. We get a 1 squared, and we're also going to get a cosine squared plus sine squared. That's another 1. So that's where the 2 comes from. And then the middle term, 2 sine t survives. So, again, this may be where you need to pause it and square this out and see if you don't get that. Yeah, I hope it's right. I think it is. So we know what this function is now, and so we plug it in. And, we could get an estimate with our calculator, but because it's in the textbook and the author says, find the arc length for this, he's not asking for an estimate. So we'll see if we can use the fundamental theorem. And if you're like me, like no immediate antiderivative comes to mind. I don't think we've ever seen it before, an antiderivative for the square root of 1 plus sine t. And I don't know that it fits, the techniques that we learned. We learned some techniques with radicals, but not with trig functions under them. And so I just kind of took a wild guess and hope that if I multiply top and bottom by the same thing, so I'm multiplying by 1, left my differential off there, then certainly we can agree that this is the same as that. I've just multiplied by 1, but this guy has a prettier form. The product of square roots is the square root of the product, so if you slip the square root outside, and then we have the difference of 2 squares, so we're going to get 1 minus sine squared, which is cosine squared. And then take the square root. Remember, it's still hanging out. Well, the square root of cosine squared is plus or minus, but from 0 to pi over 2, the cosine is always positive. So we know it has to be the positive square root. And then we have a denominator now, which we didn't have before, but it appears that the trick has worked. Because now if you look, 1 minus sine t, we can make a substitution, and there is the differential sitting right there. Maybe there's a minus sign missing, but we can get that. But there's another problem. This is a perfectly proper integral. This function, continuous, no issues. This is an improper integral because look what happens. As t approaches pi over 2, sine approaches 1. 1 minus 1 is 0. So at the upper endpoint, the function is zooming off to infinity. That makes it an improper integral. Now, because of some things we learned in, where did we learn it? Chapter 7 or 8 about improper integrals. I made kind of a big assumption here, and it's true. You might want to dig into it a little bit more. But because of the square root function, if I forget for a moment that this function is undefined and unbounded at pi over 2, then this is like a perfectly normal antiderivative. And when you find it, we're going to substitute. I didn't write the details out. I'm going to let u be 1 minus sine t, and then du is minus cosine t. So this integral becomes, ignoring all the extra sort of junk, becomes that. And when you integrate it, a wonderful thing happens. This u in the denominator, the minus 1/2 power, we raise it to plus. It moves out of the denominator. And we need to divide by the new power, so we get that. So it is an improper integral, but because of the square root function, we can evaluate, we can take the antiderivative, and it will take us out of improper territory back to proper. And so I'm just being a little bit careless. Officially, there's a limit, right? We see the problem pi over 2, and then we convert it to a limit, just like we learned in the section on improper integration. But it's going to work out okay, so we'll just talk about the details. The square root of 2 comes along for the ride. This minus 1 is from the differential. This 2 is from the antiderivative, and here's the rest of it. The square root of u, remember u was 1 minus sine t. So collect these constants, -2 square root 2, plug in pi over 2. As we said, the sign is 1, but 1 minus 1 is 0. So 0 slides in here, and when t equals 0, sign is 0. So we get -1. And thank goodness we get a minus sign to flip that, because there's no way in the world that arc length can be negative if we do the work right. This is a positive function. We assume that we're integrating from a small t value to a larger one. We have to get a positive number. And if I got these guys turned around, and so I got a negative answer, I wouldn't just assume that, well, let's ignore the sign. I mean, a negative answer would be an indication of a mistake that we made. And maybe we did just make a sign mistake and we could just ignore it, but maybe we made some other mistake. So don't, if you get a negative answer, don't just assume it's positive. Go back and find the mistake you made. Anyway, we got our answer. If we travel along this curve from this point to that point, we cover 2 square roots of 2 units. Now, there's a way we can think about, is that a reasonable answer or not? A couple ways we can do it. Is if I just travel along the y-axis from here to there, that should be a little bit less than that number. When, you know, the extra is whatever the curve takes. And the distance from here to there is 2 plus pi over 2, which is about 3.57. Sorry. Pi over 2 from here to there. So it should be 1 plus pi over 2, which is 2.57. And then my check, square root of 2 is about 1.4. So this, of course I can get a calculator out. This is about 2.8. So you can see it's just a little bit larger, just like it ought to be. So we feel super good about that answer. And this concludes new material for Calc 2 spring semester 2020. So like I said at the beginning, I will post some information about the final exam, kind of review information for you, and also details about the logistics. We'll change a few things for the final. Anyway, I'll post homework. Have fun.